All right, we are recording. Welcome everyone to Unit 4. We are starting exponential function. Well, we already did exponential functions, I guess, but the number e. I didn't stutter. The number e.
But E is a letter, Mr. Kirk. That doesn't make sense.
Right, and there's no e on this page. All right. So we're gonna
Wait,
get our brains.
There is an E on this page.
I guess you're right. It is right here.
Yeah.
And also, if I were to write my name, there'd be an E. My first name. There's an E right there. These are all letters, but we are going to learn about the number E today. All right. So before we do that, though, let's kind of activate our brains and talk about exponentials, because E is very strongly tied to the exponential function, right? And it's going to play a role in the next 5 blocks. What do we got here, Mrs. Contreras?
We have f of x is equal to 2 to the x power. So that's our base is 2, and we have our happy point that we can graph. This is a parent function that we've seen before, and there's no transformations happening to it, so we're good to go. We can just call upon our prior knowledge and hit it.
Prior knowledge. Prior knowledge. What was it? Come here, prior knowledge.
Come here, prior knowledge.
All right. That is probably the most annoying thing in the world. All right, so let's go ahead and get this horizontal asymptote. All exponentials have it, because exponentials can't be negative unless, of course, we have a shift. The happy point, as you've said, let's get 3 points. I'm a big fan of 3 points on my exponentials. I think
okay.
So.
Well, I like just if you plug in 1, that's like not too bad, right?
2.
Okay. And then should we plug in something like -1?
Yeah.
What will that do?
-1 is the reciprocator.
Reciprocator. That sounds like an MMA fighter kind of thing.
If I was a wrestler, and I mean, look at me, I could pursue that career choice if I wanted to. I would be called the reciprocator, because like just taking someone and flipping them. Oh, I feel like that'd be like the power move. All right, there we go. We got our exponential. I'm also gonna get a few more just because we can on this graph. We can get 4. Yeah. We can get 8. We can get 1/4. We can get 1/8. But whatever. Oh, that was bad. Let's try that again.
Nice.
Be as neat as one can be. This never gets. Oh, so I want to try to make it look like I care about the asymptote. Oh, I've been crabbed. You got me with the crab. Mid exponentiation. All right, we're activating our prior knowledge. We got our exponential. We've talked about some vocabulary. Base, happy point, which is a totally made up term that we use. That is not a technical term. Base is a technical term. And we got our crab mascot. What's the base over here in B?
I think our base is, well, we can think about it in 2 ways. We can think about it as our base is 1/2, and that's what we're exponentiating. Or we can think about it as our base is 2, but we are raising 2 to the -x power. So there's 2 ways I'm thinking.
There's connection between the 2 of those. I like that a lot. Cool. And like, wait, looking at this, before I even start to graph anything point-wise, 2 to the -x, that's just a reflection over the y-axis, right?
Over the y-axis, yeah.
When we negate the input, we are taking all of the inputs and moving them to the other side of the graph, of the side of the y-axis. So the happy point stays where it is. That's why it's the happy point, because it's always good. It's always there. You can rely on it. It's a good friend.
We call it like old reliable.
Old reliable. That's what we should call that point. I'm not a big fan of the term happy point. We'll call it the old reliable. You either say it like
also helps us to remember that we're plugging in 0. It's old reliable.
Yeah. Old.
Can't even say reliable.
Plugging in 0 is just a good bet. So often. There we go. All right, so we could have done this point-wise. We could have plugged in 0 into this thing, gotten 1, plugged in 1 and gotten 1/2, plugged in -1, gotten 2. No, I'm mixing up my terrible jokes. The old reciprocator. -1 is the reciprocator. 0 is old reliable. All right, we got our 2 graphs. We have activated some prior knowledge. That graph and exponents. How do you feel about these?
these seem more complicated, but definitely doable if we apply our brains.
You sound like a old like TV show on PBS, like Cyber Chase. Like we can do it.
Or like,
I believe.
or like Zoom.
Zoom, come
You
on and
remember
Zoom,
Zoom?
come on
Come
and Zoom,
on
come
and
on.
Zoom. Come on.
Absolutely.
And Zoom.
All right, but what's the happy point here?
Well, let's plug. So if we plug in 0, right, then what would happen? We
0.
have, what do we have? We have like 1/4 raised to like 5th power and times -2. So that's like not ideal. But what would make our exponent 0?
That's the
To
happy.
plug in the oh reliable.
Oh, reliable. So in this case, we want O reliable. So I think we need to give the function -5 to get O reliable.
I think so.
-5, 1, 2, 3, 4, 5. -5 over here. That's not the point, but we're dealing with this tick mark. When we plug it in, 1/4 to the 0 is 1. 1 times -2 is -2. Plus 6 is 4.
4.
Cool. Right. Instead of thinking about, well, I think that's a really important point to get. The happy point, the O reliable point. But let's start thinking about as transformations as well, right? Like what's happening to the asymptote? It's at y equals 0.
And then it gets shifted up 6.
Right? Like it gets a bunch of things happen to it, but the only thing that really changes the horizontal line is that 6. The 5 shifts it left and right. Nothing happens to a horizontal line. The -2 reflects it and dilates it, but it's 0. It doesn't get stretched away. 6 is the only thing that's doing anything. 1, 2, 3, 4, 5, 6. So O reliable, happy point, is beneath the asymptote.
But that makes sense because we have the -2 that's a reflection across the horizontal axis and a dilation. So it also makes sense that it's 2 off from where our asymptote is.
I think the first thing I would do,
Cool.
and you can have different steps, is find O reliable. I guess it'd be like that, right? No, it'd be like this. O. No, it'd be like this. O reliable.
It's like
And
more letters, more characters than
old. Find O reliable. And then graph the asymptote. I don't know. I like giving now, it was a thing I did a lot last year. I haven't done it much this year, but I like giving 3-step processes to everything I do in my life. So what would the third step and final step be for graphing an exponential?
Find more points and connect them.
Yeah, get 2 more points. I guess you could only do like 1 more point. You could do 10 more points. Get 2 more points. I like 2. Personal preference. What are some good points to plug into this thing?
Well, we have like 1/4. What is that?
Sorry. Reciprocator. Come on.
Oh, I see. Okay. Anyway, so what can we plug in to raise 1/4 to some like nice power?
Well, I'm sticking with my guns. I'm saying -6.
Okay, -6. So if we plug in -6, then what do we get? We get -1 as our exponent. And then it's a reciprocator. Or 1/4, so we get 4. Then 4 times -2 is -8. -8 plus 6 is -2.
So -6 comma -2?
I think so.
Boom. And then, I don't know, you want to do the last one?
Sure, let's see. What's nice? I want like something small. Like something closer to the asymptote. Well, what happens if we do plug in like 0?
Plug in 0.
It's not very nice.
But I think we can kind of like work our way towards it. Like if we want to approximate, right? 0 to the 0 plus 5 is 5. 1/4 to the 5th is a very small number, right? And then a very small number times -2 is a very small negative number, right?
A slightly less small negative.
Yeah. So just less than 0. So we're like right here. And then if we add 6 to it, we're going to be like just right here.
Yeah, that sounds good.
I don't think that's completely unreasonable. Plugging in 0. There's a good one. I think another good one would have been -4, right?
Yeah. Because then we just get 2 times 1/4, which is an easier fraction to handle.
Yeah. There we go. I vote we leave this problem over here as a quiz question. Maybe ask something like, where's its asymptote? Or what's its vertical shift? Or where does the happy point exist? The all reliable. Cool?
Those are all good options.
Yeah. Maybe we'll ask them all.
That
Like
probably
right back to
requires.
back.
It's really annoying though when it's like back to back questions because
Mhm.
sometimes it just doesn't pop up. So maybe not. But
Mhm.
I would like to note that on this one it might help to factor what's in the exponent so that you can see a little bit more clearly what's happening to your inputs.
Mm-hmm. And a while ago, I think we talked about how, like, when doing transformations, it's nice to be in that factor form. Because when you're dealing with inside the function, you want to do things backwards. Right? So if I have -2 times x plus 3, I think it should be a -3. And then I start to solve an inequality. We're throwing this way back to transformations. I don't know, 0 to 10. I'm just making up some numbers. The first thing I'm going to do is divide by -2. So that's the first transformation that happens. A shrink 1/2 and a reflection. So I don't know. Factoring, I agree, 100%. Factor, do it. Don't think about doing it, do it.
Or doing it.
Oh, that was the most epic segue I think that there has ever been. Because we have tailored these word problems today to be themed. What's it called? I'm having
DuckTales.
DuckTales. Woo! DuckTales. All right. Although, how often is Donald Duck in DuckTales? Is he in every episode?
I don't think so.
Or do you watch the new series, or are you? Or
Yes,
it's very
it
good.
is so fun.
I'm also a big fan of voice actors, and I have a lot of there's a lot of voice actors that are in it that are really good voice actors. All right, let's do some word problems.
Right.
Do you want to read it, or do you want me to read it?
Donald Duck recently bought his first cell phone. The salesman, Mark Beeks, told him that in the year 1999, only 5 million Americans had cell phones. During the next 6 years, the number of cell phone owners increased by an average of 60% each year. Crab. Part A. Write a model giving the number of cell phone owners, C, in millions, the unit we're working with is millions, of cell phone owners T years after 1999, and how many Americans own cell phones in 2003, which might be before you all were born.
I think it is. I think, yeah, for sure. That's weird to think
Anyway.
about. Man, do you remember when you were a kid and you had to like wait for the phone, first of all, because someone else might have been using it? Or if you picked up the phone, it messed up the internet connection.
Yeah, and then it was the horrible sound of like signing on, just like.
And you also knew the phone numbers of your friends.
Mhm.
Not anymore.
Yeah,
Although I
have
do think
mates
it's
that had
important to
phone numbers.
memorize certain numbers.
Yes.
Yeah.
Your parents or whoever's responsible for you, and any siblings or friend people who can like help you out for things.
I feel like it's a big badge of honor for a friend to know your phone number.
Mm.
Like, dang, that's a good friend. If they know your phone number, that's a good friend. Do you know my phone number?
I don't actually.
Oh, that means you're a bad friend.
They only interact with you through mainly the internet.
I know. All right. So we got Donald Duck. He's finally gotten around to buying a cell phone. I think these problems are best done using a chart. I think these problems are best done using a chart. Just like we did when we were doing when did we last use a chart? Optimization.
Mm-hmm.
I think
Organize our thoughts. Think about what variables we're using.
I think
like step by step.
Often it's the case that like you get given a formula and then you're just asked to plug things in, which is like good and bad. I mean, it's nice to have formulas, but I'd rather just like be able to generate the formula on a whim. I think that's what we're going to do here. Let's like make a chart. All right, so t is going to be our variable, right? Is that a reasonable t?
Yeah.
Because we're dealing with time. That's our variable. And then c is our amount of cell phones.
Mm-hmm.
That's our dependent variable. And we'll answer A and B later on. Let's look at this. So how many cell phones do we have Well, so what is T? What is T? I think it's
T
more
is
than
years after 1999. So 1999 is T0.
And how many cell phones exist? Or how many, well, I don't know how many cell phones exist. How many Americans own cell phones in 1999?
Well, according to this, and it's laggy, bam, in 1999, only 5 million Americans had cell phones. So we got our C is in millions, so it's a 5.
Awesome. Let's not write 6 zeros. Cool. All right. 1 year later, there's on average, this is all just speculation. There's a 60% increase. So our base, our initial amount is 5, and we are increasing 60%. So what is that? 5 times 0.6?
Yeah, because it's 60% of the previous year.
Mm-hmm. And so with that said, let's simplify this thing. I see a GCF. Factoring out of 5 out of 5 is a 1. Factoring out of 5 out of 5 times 0.6 is 0.6. I can simplify this further. PEMDAS. Let's get the thing in the parenthesis going. 1 year after 1999, I can use the number 1.6 to get my new number. I can multiply 5 times 1.6 to get that new value. I don't know what that is, but let's keep doing this and see if we can generate a formula for T years. What's happening after 2 years?
After 2 years, you're taking what happened in year 1, which is the year 2000. So 5 times 1.6. And then you're adding on that previous amount times 0.6, which is 60% of the previous year.
All right, so these are all based on the previous year, not the initial year, the previous year. I see another GCF. I actually see 2 GCFs. There's a 5 in common in both these two numbers. But there's also a 1.6 common in between both these numbers. And then by doing factoring, I take 5 times 1.6 out, and I can take this 0.6. And then I believe I get 5 times 1.6 times 1.6.
Can we simplify that?
I think so, right? That's like the definition of exponentiation. It's almost as if we were graphing exponential functions a second ago on purpose.
Wild.
All right, so 5 times 1. So these are exponential models. What happens 3 years after?
3 years after 1999. So you take the previous year, year 2, so that's 5 times 1.6 squared. Then you add 5 times 1.6 squared, which is the previous year, times 0.6, which is 60% of the previous year's amount.
Awesome. And I think
GC.
I'm just gonna jump to the final line. Is that cool?
Oh,
I think the pattern has now been well established. So we have a 0. So I guess you could say there's a 1.6 to the 0 here.
Ooh.
We have a 1. There's a 1 there. There's a 2. There's a 2 there. There's a 3. There's a 3 there. How about, I've kind of run out of room. How about T years?
T years, you just take 5 times 1.6 raised to the T power.
Boom. F of T is equal to 5 times 1.6 to the T.
Is it F or is it C?
It's totally C.
Because the output that we're getting is the number of cell phone users, C for cell phone, in millions.
Okay. The number of cell phones in millions as a function of time is what we're saying here. So I think we have our model. We've done A. This is A.
Nice.
And then B, underneath the crab. Oh, I like that you added some texture to my crab. That was like I just noticed. Anyways, how many Americans own cell phones in 2003?
Well, 2003 is how many years after 1999? I think it's 4 years.
In 2000, 2001, 2002, 2003. I think we could just do 2003 minus 1999 if we wanted.
Yes.
Yes. So C of 4 is going to give us our answer. And I actually don't have a calculator. So I don't know what this is.
I can figure that out. Oh man, I wish we had MATLAB up. According to the calculator, it is 32.768
Only 32 people owned. Cell phones
million.
Million people. And then if we can model now, what happens when we plug in 21?
Wow. 96,714 million, which is 96
Billion, I think?
billion?
I mean, I guess maybe.
What? No.
Right?
There's not 96 million people in the United States.
You're right. You're totally right. I was getting my numbers
Billion.
wrong.
Yeah.
Yeah.
There's what, like 3?
I think there's 7 billion people in the world right now.
Sure.
Or roughly, maybe between 7 and 10. I could be wrong.
Sounds great.
Well, according to our model, and I think it's clear that models are not perfect. This is a short-term model. It would be very poorly, it would not be effective for large values of t being 21 being large. All right, let's do some more. And you know what? Do you want to leave two for the viewer?
The one about Launchpad?
Yeah, so we kind of need to explain what's happening in this one before we move on. We could also do it.
I think just talking through it, I think it's good.
Yeah.
But not doing it.
So Launchpad McQuack, character from the show, recently cashed in his 401k to buy a Thunderquack for $100,000. Each year, the value of the airplane, so the Thunderquack as an airplane, depreciates 15%. Write an equation that models the value v. Did you just Launchpad McQuack me?
I did.
I'm obsessed. That's hilarious. Depreciate. So we're losing value. Write an equation that models the value of the Thunderquack 2 years after it was purchased, and how much will the plane be worth after 6 years? So this is a very similar problem. The difference is we're depreciating. Is that the Thunderquack?
That's the Thunderquack.
Excellent.
The problem here, though, is we want to give you unsolicited life advice. We want to give you advice of like what not to do with your 401k. 401ks are for retirement. Do not cash them in to buy an airplane. It is not a good idea.
Look at that guy. He's not ready to retire. Don't cash in your 401k. Yeah, 401k is a savings account that you pay into as you work. But
don't cash it in for an airplane.
No,
that's a want. That's not a need.
Slowly take money out of it when you retire, and then that'll take you to the good old age of when you die. That's the point of the 401k, to save money for retirement.
There are other options, though.
Yeah. 401ks are a private thing, I think. 403bs are the public version of a 401k, and there's also things called Roth IRAs. Look these up. Journal about it. This is like, they always complain, I didn't learn enough about money in high school. You should look up what a 401k is. Look up what a Roth IRA is. 401k, Roth IRA. Anyways, we're starting with 100,000 here, and we're depreciating 15%. So we start with 100,000, we subtract 15% on that. This is to get to year number 1. This is year number 0. This is to get to year number 1. And then this ends up being 100,000 times 0.85. So instead of having a number larger than 1, we have a number smaller than 1. And we're depreciating. We're getting less and less and less. All right, so we're not going to do this entire problem, but you can imagine what the formula is going to look like. 100,000 times 0.85 to the t. And that'll tell you, so plug in 6, and then you're going to know how much that plane is worth. Some things appreciate in value over time. Vehicles tend to depreciate, which is unfortunate for people like me who just bought a car. Vehicles are not investments.
Nope.
With few exceptions. A classic car might appreciate in value. I don't know much about the classic cars though, so I could be a little bit wrong. If anyone has any like parents or guardians or siblings that collect cars, maybe you could enlighten us in class. Anyways, I'm going fishing. I might catch someone there.
Yeah.
All right, I want to do number 3 though. When a certain medicine enters the bloodstream, it gradually dilutes, decreasing exponentially with a half-life of 3 days. This is the reason why I want to talk about it.
What's a half-life, Mr. Kirk?
So half-life is the time it takes. Usually things that help me out here. Like what has half-life?
Radioactive decay tends to be counted in half-lives.
So half-life
and then
is
medicine things.
Yeah. It is the time it takes for a substance to decay to half its size. So in this case, we have a 50 milliliter dose of a medicine. We're being told that it has a half-life of 3 days. The makeup of the substance determines its half-life. Some things have tremendously long half-lives. Medicine here has 3-day half-life, which means after 3 days, we're going to have half the amount that we had 3 days prior. So just like the previous problems, the next iteration of how much you have is dependent not on the initial amount, but on the previous amount. I guess that's wrong. It is dependent on the initial amount, but we calculate it based on the previous amount.
Of the step before.
Yeah.
So it's kind of like in, what is it? There's something recursion in computer science.
Yeah,
where you're
recursive
looking
rule.
at just the previous step, not necessarily the very beginning.
Let's build an explicit rule using a recursive pattern. So we start with 50 milliliters. So at time 0, we have, are we given a is our dependent variable. We start with 0 and we have 50 milliliters. I could put a ml here. And so I could write 1 here, but I'm not given how much of the dose is left after 1 day. I'm given how much is left after 3 days.
So after 3 days, the amount that's left is half of at day 0. So that's 50 times 0.5 or 50 times a half, whichever.
Yeah, and we're using, because we're decreasing, because one could say depreciating. I wouldn't necessarily use that term in this scenario, but we can think about it like we did in number 2. We're subtracting. And then we do a little bit of factoring. We are going to get 50 times 1 minus 1/2, which just happens to be 50 times 1/2. So for half-life, that base that we've been generating in these problems, it's going to be 1/2 to the 1. After 6 days, we're going to have 50 times 1/2 to the 2. After 9 days, 50 to the 1/2 to the 3. How about after t days?
Well, after t days, that's tricky, right? Because we've been working with multiples of 3. So we need to think about how to go backwards from having like our pattern of when we plug in 3, we get out 1 as our exponent. We plug in 6, we get out 2 as our exponent. So I think there's some sort of division. It seems to be by 3, which is the number of days of our half-life.
So when we plug in 12, what do we want to get?
We want 4.
So
because that's 4 iterations of the half-life periods.
So I think we plug in 12. Did you say this? We need to divide by 3?
I think so. Might have said it quickly.
Yeah, sorry. And so I think that might be it. And we can check ourselves, right? If we plug in 0, we get, this is what you were saying. Plug in 0, we get 0. Plug in 1, we get, if we plug in 3, we get 1. If we plug in 6, we get 2. If we plug in 9, we get 3. If we plug in 12, we're going to get 4. If we plug in, what do we want, 30? We should expect, if the half-life of 3, we should have halved 10 times. And I believe this formula does the job. A sub t is equal to 50 times 1/2 to the t divided by 3. for B, we can plug in 10 and get, 30, and get that 10 iterations of half-life.
Which I think is 0.0488.
And at some point, this medicine is going to be ineffective because it's been diluted so much and it's left the body in different ways. Sweat. I'll let you guys, think about other ways that liquids can leave the body. Boom.
Cool. So we talked about half-life, and so we used that base that we were using before, which is nice. But I wonder if, like, with this idea of interest, if it matters, like, how often the interest is happening.
Oh, yeah, because we have these, like, I think you're getting at this, right?
Yeah. So if we were thinking about retirement, right, because we were being responsible, and so we're like, if we suppose we deposit $1 into an account that pays 100% annual interest, that's amazing.
That doesn't exist, but it's a good thought experiment.
How much money is in the account after 1 year if the bank gives you your interest once a year annually, or different amounts of time that we're going to figure out?
Yeah. So I think the important thing is in proceeding, the bank is giving you 100%. We're going to look at if that bank breaks up that 100% into different increments, right? Like if you take all the 100 at the end, or if you take 50 halfway and then 50 at the end, or if you take quarterly, if you take 25, 25, 25, 25, does how you take your percentages change the amount that you get? Let's do it. Let's just like punch it out.
All right.
So the same problem as we just did. Our principal amount, our initial amount, is $1, right?
Yep.
And then we need to.
We have that amount plus 100%, which is 1. Then we do that once.
Yeah, we do it once. I'm going to divide it into 1. I think this will make more sense as we look at more of these. And then we're doing that once.
One time.
We're going to have, if I go back up to this first chart that we did, we're multiplying 1.6 a bunch of times. In this first example, we're only doing it once. So 1 times 1 plus 1 over 1 to the 1, what is that?
1. Just kidding. It's 2.
It's 2, right? 1 plus 1, 2. 2 to the 1 is 2 times 1 is 2. So 2. So if you $1 compounded annually at 100%, you have $2 at the end of the year. It's a pretty solid bank.
Yeah.
All right, semi-annually. Let's look at this. The principal amount.
Twice in 1 year that we're getting our interest paid out. So principal amount is $1 because that's what we put in. And then we have that amount plus 100%, right? Divided by 2 because we're taking it twice in the year. And we're doing 50%.
Yeah. We're getting 50% twice. What does that end to be?
1 plus 1/2 is 3/2. Squared is
9/4.
9/4.
It's 2.25.
2.25.
Ooh, so it looks like if you take your percentages in increments rather than one lump sum, you'll get more. Can you think of a reason why that might happen?
Well, because so say it's like January you start it, and so then in July you're getting an increase in the amount. That means that from July to the next January, you're going to get, or I guess the end of December, you're going to get interest on what you've gotten interest from.
If you get your money halfway through, that new money can make money. This is all based on the idea that, it's all based on the idea that the banks are taking your money and they're doing things with it. They're investing it. They're doing things that make money with, and then they're giving you a cut of that. All right, what if we do this 4 times during the year? We take 25% 4 times.
So then we have 1/4 raising to the 4th, and that's a different number.
while you calculate that, we're still getting 100% at the end of the year. We're taking our money out, putting it back in, taking our money out, putting it back in, so that that new money can accrue money. What do we end up getting there?
$2.44, and I guess they'll probably round down because 2.441.
Yeah. So banks always round down. I actually believe that's a thing. I mean, you gotta live with it. Banks round down. All right. Monthly. How many months are in a year?
Ooh, there's 12. I knew that. Off the top of my head, I knew that.
Nice. Except in leap years, right? There's 13 months.
No, that's in different calendar systems. There's a leap month. Yeah. But I think there's something with like there's a leap month every so many years for like some calendar systems. But then someone wrote a calendar and some people journal about it. I forgot who it was, but they made a calendar. It was some Iranian, I think, mathematician who made a calendar that you didn't need any leap anything. Like it was a fantastic standalone calendar.
I think it's about time that we move on from the Gregorian calendar. Like, come on. But do you know about leap seconds? We all know about leap days. We have it once every 4 years, February 29th. Leap seconds are a thing. Look it up. I think it happens every 100 years. I could be wrong. Leap seconds. Anyways, what is 1 plus 1/12 to the 12th?
2.613.
1, 3. So I'm going to go with the 1. Do you notice that we are slowing down in our increasing?
Yeah, because it went up by a quarter, and then it went up by
literally a quarter.
Literally a quarter.
Like a flip, like heads or tails quarter. Okay.
And then went up by 19 cents, and now it's up by less than that.
Yeah, 19, and then I think 16, maybe. No, 17. All right, daily.
Daily. How many days are in a year?
365.25.
Oh wow.
I think we're going with the leap year theme here, so let's just do it.
So we got 2.71457.
4, so I'm gonna leave it at the 7-1. Okay. Actually, no, I'm gonna add those numbers because I have this intuition that well, not intuition, but I have this goal I'm getting to. 2.71457.
1799.
1799.
Yep.
Cool. All right. Hourly. Ooh. Let's like forget about the 0.25 because that sounds kind of annoying. How many hours are in a year? 24 hours in a day.
24 hours in a day.
So
times
20,
365. Yeah. So whatever that is.
I'm just gonna be lazy.
Yeah, and that's how I did it in Desmos just now to calculate this.
All right. So that's not 24.365. That is 24 times 365, and that ends up being
2.71812669162.
62.
Yep.
Interesting. So like these numbers are the same. These numbers have always been the same. We've never been able to get past $2, but we've started to slow down. We have a 7, we have a 1, we have a 4, then we have an 8. So we increased by what is that? A 0.4 of a penny. There used to be an increment. There used to be a denomination of coin that was I believe half a penny.
Wow.
Minutely. 1 times 1 plus 1 over.
This is a rent song, right? 125,600.
520. 520. Oh man, our musical theater students are probably yelling at us right now.
It's okay.
500. Oh shoot, man! I even like listened to Rent recently.
You listened to Rent? You didn't watch it?
I mean,
you just like
when I'm driving in the car, throw some musical theater on.
Okay, 525,600.
5,600 minutes. 525,000 moments.
600 minutes.
All right. So what this is saying is, that's a 100. What this is saying is we're taking our 100%. We're dividing it into that many percents. We're getting each of those incrementally that many times. So we're taking our money out. Every minute, we're taking our money out, putting it back in, taking money out, putting it back in. It's a very extensive process. Guess what? The banks do this for you. You don't have to do it physically. What do you end up getting?
2.718
Okay.
to
Oh, so that
7
number changed. 7.
9 2 4 2 6 7.
Let's do one more. Secondly.
All right. Secondly.
All right, so that number times 60.
Yep. Which is, if you wanted to know, it's 31,536,000. Yep.
And we get 2.718.
2
Oh, okay.
8
Oh, that's where it changes.
1
1.
7 7 8 4 7.
Boom. Cool. So we got to daily. I granted we did jump from 12 to 365. But we got to daily, and then we've kind of like leveled off at 2.718. That seems important.
It does.
2.718 is
Pi.
I feel like there's a relationship between e and pi. Fun fact, e to the I pi, that's -1 or +1 is equal to 0. It's called Euler's formula.
Euler's formula.
But
Don't say
2.7
Euler.
Euler. You wouldn't
Euler.
say Euclid. It's Euclid. Anyways, this is the number I referenced at the beginning. This is the number e. Well, this is not the number e. This is approximately the number e. The number e is defined as this right here. Let me zoom in. The number e is 1 plus 1 over n to the n. That's what we've been dealing with. 1 times 1 plus 1 divided by that number that we're dividing 1 up into, 100%, raised to the amount of times you're getting it. As we got bigger and bigger and bigger, when we got to 31 million, we got really close to 2.718. We've done this before. I'm going to get rid of, first of all, I'm going to get rid of this 1 because we don't really need it. The limit as n goes to infinity, as n gets bigger and bigger and bigger and bigger, this number gets closer and closer and closer. One could say as close as you want. Do you want to be 0.0000001? Just go out far enough. This gets as close as you want to this irrational number e. Right, we've used limit notation before, so that's why I threw it in there. But you can also, just as n goes to infinity, this number gets closer and closer to e. And this is a good approximation of e here, but just like 3.14 is usually good enough for government work, and that's what we are, we're public school. 2.718 is good enough for e, at least with what we're doing. If you need more accuracy, you just go further out. But 2.718, the 1,000th place is pretty good. Let me zoom back out. 2.718, 2.718, 2.718, 2.718. Get that number into your brain, just like 3.14 is in your brain. You know, everyone makes a big deal about Pi Day. I think we should celebrate E Day more often.
E Day. February 7th. We can try it.
I think we should make a big deal about E. I don't know.
Pencil it in.
Pencil it in.
It's on a Sunday.
Make Math Honor Society figure that out.
But it's on a Sunday. Can't do it.
Well, sometimes Pi Day is on a Saturday and we still celebrate on the Friday.
Yeah, that's true. Pi Day is on Friday. Or on a Sunday this year?
When do we celebrate it? Anyways, we'll let Math Honor Society figure that one out. All right, so we've been dealing with the compound interest formula. That's this thing right here. All right, I just want to provide this with a little bit of context before we move on. This is what we've been using this entire class. We just haven't been writing the formula down. I am super anti-formula. Just know how to generate it, and you'll get the right answer every time. Your principal amount, that was like the $100,000 that, what's the duck's name that bought the airplane? The Thunder.
Launchpad.
Launchpad, that principal amount, $100,000. Then we have 1, which represents that initial $100,000. And then maybe the rate is negative, maybe it's positive. Right? When we were dealing with the problems earlier, that's all we had to deal with, the rate, because it was happening once a year. But if it happens multiple years, like we just dealt with the 100%, you might divide that percentage into equal increments and then get that increment over a span of time. So if you divide your 100% into 4, you're going to get 25% 4 times. So you need the 1/4, and you need to multiply 4 times. That's what this compound interest formula is saying. Right? So you can learn this formula, or you could just make a little chart, get your answer the old-fashioned way. Right? Formulas are useful, but the reason why the formula is here is because I want to come up with a formula that we do need that involves E.
Well, we're letting n go to infinity, so I feel like we need to think about how that connects with what we have up above a little bit in our page with E, our definition of E.
We got 1 plus 1 over n to the n. That's E. How can we turn this thing down here into 1 over 1 plus 1 over n to the n? Maybe not n, maybe a new variable. But we need 1 plus 1 over something to the same something. If that thing's going to infinity, E pops into existence. How can we get E out?
What if he used a U substitution?
Okay.
What if we change the variables that we're working with? To simplify, to draw together those two, the R and the N, so that we just have to work with one thing.
Well, so I love that idea. Can we get a numerator of 1 here first?
Yes.
Yeah, because that's what we want E. We want a numerator of 1. So A is equal to P times 1 plus. How can I get a numerator of 1?
Reciprocator.
You had like that. Oh, okay. Wait, so 1 over the reciprocal, right? N over R. Okay. And you want to use U substitution. What should we set U to be?
Well, can we say, because we want the denominator to go to infinity, can we say that U is the denominator N over R?
So you want to say U is the denominator, the N over R. Okay. I literally repeated what you said, sorry.
It's cool.
It, like what you said like slowly crept into my brain. Cool. All right, so that is U. Let's go ahead and add that to our page. Now I have a question. We're sending N off to infinity. But we're getting rid of our N's in this pursuit of 1 plus 1 over U to the U. As N goes to infinity, what happens to U?
U also goes to infinity because N is growing our numerator really, really big. So the numerator of our number is a really big number divided by some R, which, sure, okay, it's a number.
It's fixed, right?
It's fixed. So then we have U also goes to infinity.
So, okay, this is good because we need the U to go to infinity as well. So as N goes to infinity, U is also going to infinity. So if we can get 1 plus 1 over U to the U, then we can have an E as N goes to infinity. How can I get a U in the numerator?
We can take that N and we can substitute, we can rearrange what our U equation is. So we can say that U times R equals N.
U times, you're going to multiply both sides by R. U times R is equal to N.
And then
Let me actually
that in.
make it really obvious. U is equal to N over R times R on both sides. U times R is equal to N. Okay.
So now we have N in terms of U and R.
Okay.
So just put that in for N over here.
If you throw a Z there and make it an E, you have Ertz. Go Birds.
Go Eagles.
If you get rid of the R and you put a Z, you have a chip brand. Okay, I'll stop. Okay, so we have 1 plus 1 over u to the u. Can I kind of break off that u? Does this break any rules?
Nope, not at all.
That's like
Right? Because a power to a power is totally fine
mm-hmm.
for exponent rules.
And so we're sending, so as n goes to infinity, u goes to infinity. So we're sending u to infinity, 1 plus 1 over infinity to the infinity and beyond. Is e, right? Well, not to the infinity. We can't raise things literally to the infinity. It's not a number. But as we get closer and closer to infinity, we're getting closer and closer to this value e. This baby concept of a limit. So we have, this thing is e to the rt. Let's get rid of those brackets. Pe to the rt.
Endearingly referred to as pert.
Ugh, pert. Pe to the rt. I'd rather just say pe to the rt.
It's pretty good, though.
Peer to. This is bad. Pert. So this is. So we have the compound interest formula. What do we do when we make that n massively big? It's possible, first off, and the n actually goes away.
Cool.
Which makes sense, right? Because it was infinity. Yeah. As n goes to infinity, it kind of disappears, becomes irrelevant, and we get closer to this number 2.718. But we also have the rate to the t. So the difference between the compound and the continuous formulas, compound has an n in the numerator, in the exponent. Continuous has an r in the exponent. That's a common mistake when people are using the formulas. That's why I like to avoid the formulas at all costs. We cannot with PERT. Kind of need the formula. But with the compound interest, we can just like big brain it out.
See you using slang, trying to be culturally relevant, Mr. Pert.
No. Yeah. All right.
We got a word problem and a graph.
Yeah. Where are we at on time? Do you know?
We are lagging.
All right, we're slagging. Why don't we call it quits here and throw this one on the problem set?
Hey, love it.
Because we don't want you guys
to graph though. Probably graph number 5.
Yeah, we can do we can do that one real quick. We'll do one for you guys, but we'll leave that word problem for you. We don't want to make you mindlessly watch a video for too long.
But it is piecewise. Mm-hmm. That is our hint to you.
Yeah,
piecewise
yeah.
it.
Did I spell piecewise right?
Yeah, it looks great. I can't really tell what you're doing in the middle. It looks like peak.
Good. If your handwriting's bad enough, they'll not know you're wrong. Don't copy my mistake. All right. Anyways, we do want to do this one though, just so everyone's cool. E, contrary to popular belief, is a number in math, not just a letter. So when you see e to the x, you need to think that number. 2.718, 2.718, 2.718, 2. We should make a song. We never forget 2.718. How do people know 3.14 so well? Repetition.
Pure repetition.
Yeah.
But also there's that thing where it's like 3.14 and then that like reflects the like PI.
Yeah. I do want to say that we don't want to get rid of that 8 because if we get rid of that 8 and we go 2.71, we're like off by a significant amount. So let's get that third decimal. We're going to go to the 1,000th here, even though with pi we only go to the 100th place. All right. So happy Thanksgiving, by the way. Pi reminds me of you just reflected 3.14 over a vertical axis to get pi. I like that a lot. That almost went over my head. All right, 2.718, that is a number. But the great thing about this is what is the most powerful thing in graphing exponents?
Reliable.
Reliable. So if you plug in 0, e to the 0, doesn't matter what it is, 2.718, irrational, goes on forever. Who cares? It's still 1. E to the 0. How about, what's the reciprocal of 2.718?
Like slightly less than a half.
Slightly less than a half? Fair enough. a number slightly larger than, so if I have 2.718, if I reciprocate these, you got to switch the sign.
The inequality sign.
Yeah, the inequality sign, not the plus or minus sign. Yes, it's a little bit less than a half, and then 2.718 right there. We got 3 points.
Boom. Asymptote doesn't change though, right? It's just
no vertical shift, remember?
It's a horizontal asymptote.
Yeah.
Sorry.
No vertical shift. All right, that's a good place to stop.
Cool.
Yeah. Icebreaker.
What was your most impressive cooking fail?
Oh, my most impressive cooking fail? Wait, can you go first so I can have some time to think?
So I have a few, but they all involve just like not doing things right, which I guess is all cooking fails. But one was I accidentally punched in 10 minutes instead of 1 minute on trying to microwave steamed buns. It was like very smoky. It was pretty sad. And I've also we're making tamales, didn't put enough water in the steamer, so then steamed the pot dry, kind of ruined the pot. Yeah, took a little while to get that out.
I got like a few things that come to mind. One was in college. And I think this is a really good question because people that are scared of cooking, like you need to be okay with failure because you're gonna fail when you cook like a lot. I remember accidentally turning the pepper and the top coming off and an entire thing of pepper falling into the eggs I was making.
Wow.
I still ate it.
Did you like cry because it was like so spicy?
No, it was just disgusting.
Okay, that's good.
But I wanted the nourishment, you know. And another epic fail was baking bread is a challenging pastime, and you most definitely, if you're trying to get into bread making and specifically sourdough bread making, you got to be ready to fail a lot. And I get very frustrated when dough is sticky because like once dough is sticky, like you can throw some more flour in there, but it's might be gone. So I have been in a rage, like throwing dough across the room like a barbarian. So
To
I
knead
guess
it, or just because you're upset at it?
because I'm upset. I've thrown dough aggressively into the trash can before.
Wow.
It's really
but intense.
You know, sometimes you just got to be okay with starting over. But those are the ones that come to mind. I'm sure there's been a more epic fail. If Mary Kate was near me, I'd ask her. I'm sure she would know.
Your producer. Right?
Yeah, my producer. Yeah. Cool. Yeah, that's a good video. I'm happy with how that turned out. All right, ready?
Yep.